So here's a statement that uses a temporary register and a save register. So we have to compute f as the sum of g plus h minus the difference of the sum of I plus j. So many possible solutions. One possible solution is to add together S1 and S2 here in this first machine's instruction, and then add together S3 and S4. Why? Because someone told you that the symbol table was defined so that S3 and S4 contained I and J. I and J have to be added and subtracted from what? The sum of G plus H. This was the destination for the output of that instruction. It's stored in T0. So then I can subtract T0 minus T1. That result goes in S0. S0 we said was F. And we computed now, so F contains the output of G plus H minus the sum of I and J. So what we're seeing here is one possible assembly language realization is what the machine actually executes, right? To realize this C statement, is there another one that you can propose that would also work? Just what we covered so far. Another sequence, I'll give you a hint, another sequence of instructions that can realize the same result. So another choice, you're going to say, well, it doesn't matter too much. Well, it may matter if I have two adder units and one is busy doing something and maybe they're different types of adder. We haven't made it that complicated yet, but sometimes interchanging these makes a difference in the execution, time or delay. Another way to do this, right, I can move this up here. Is the program still going to run correct? Does it have the same semantics, the same input-output behavior? Yeah. Can I move this up here, though? No. Okay. So why do we learn assembly language? Because we learn what the hardware actually does. Because sometimes it matters when our program executes. And we're going to see, to design these units, right, add, subtractor, part of the ALUs, part of the data path, we have to know what these take in as inputs, how they work, what's the concept. So we cover each one of these, and we'll learn about 20 different instructions. So let's learn another instruction. Here's a load instruction. We said load was getting data into a register. Well, we have a few different types of load. One that you use a lot is load immediate. Load immediate is for loading a constant. Okay, so immediate is a fancy, is immediate value, right? Is a fancy word for constant. So for example, if I want to load this register, V0, with a value which is a constant 4, is that decimal 4 or is that any other type of 4? It's decimal. Decimal 4, I want to load 4 into this register. Here's one way to do it, is the LI instruction. You can see LI accepts many operand types. Here's a decimal 4 here. If you want to load it with hex, because you're just using hex already, you can use 0x. Suppose you want to load it with the bit value sequence for a character. You can put single quotes, and the assembler will translate this from a character on the screen to a sequence of bits which correspond to the letter. We'll see more examples. If I want to depict how the information is flowing, go back to our abstraction. Processor is this box. Memory is here. These are the cell contents. Okay, I broke them into bytes, right? Remember we have 4 bytes per word. Each byte has a separate address because memory is byte addressable. Now we see it. Memory is byte addressable. Each memory location, which is 1 byte, has a separate address, and the address goes up by 1 as the bytes go up by 1. When we do load immediate, since this is a constant, we don't have to transfer any data between processor and memory. We see in some other choices we move data back and forth. We're going to see other cases where we do transfer information. But load immediate is loading a constant. We said constants can be part of the instruction. We'll show you the bits later. Since it's a constant, we don't have to transfer any information from memory. We're just loading a value into a register. But it's a good question. We have here 4 bytes to make a 32-bit register. Does the value of 3 get loaded on the right side or get loaded on the left side? Right. We load on the right side, and unless we say otherwise, our convention, practically every data sheet you pick up, unless they tell you otherwise, which is very rare, this is the least significant byte here, and this is the most significant byte on the left, just like we write a number. Okay, so what's another type of load? Sometimes we want to load a constant, other times we want to load an address. And you're going to say, okay, well, why? We're going to give you an example on the next slide. Well, we want to load an address. There's another instruction called LA. You're going to say, all right, I'm seeing the pattern here. They're called mnemonics. What's a mnemonic?
Something to remember stuff?
Yeah, mnemonic is a memory aid. It's something that helps you remember. It can be an acronym, but not necessarily. In this case, it is an acronym, load address, but sometimes they're kind of squashed up, partial mixed up thing, you know. Sometimes we have add immediate. It's actually the word add, then the I, right? What's a mnemonic for colors of the spectrum? Roy G. Biv, right? It's a mnemonic. It helps us remember something. So LA helps us remember load address. It's for the programmer. The machine can't execute LA. It gets translated from assembly to a sequence of bits. That's what Mars is going to do for you. You're going to write some assembly, or simple ones like we're doing today. You put it in Mars, you say assemble, it converts it to the bit sequence so the machine can actually run it. What sequence of bits? Well, the ones that go into the control unit like we saw in the animation that do what? Figure out what to do with that instruction. Each instruction has a different sequence of bits. That was von Neumann's store program concept. So what does LA do? LA loads an address into a register. You're going to say, well, what is that? Well, sometimes we need to know the value. Sometimes we want a constant to go into a register. Sometimes we want a value, which is over here in the memory. Right? Memory has two components, address, and this is the data. There's a value that's at that address, right? So this is the post office box, and this is what's inside that P.O. box. They can have different capacities depending on what money you pay, right? You can get a different post office box. Every post office box has an address. So here I want to load the address into a register. That's like a pointer in C. I want to get the address of the data. It's a pointer. I want to get the address of the data and put that into a register. Our machine registers are actually variables. So this particular case, these are just made up numbers, but address 101, that's a hexadecimal number. And we're going to see that gets loaded in that sequence of bits. So when do you have to load an address? When do you have to load a constant? Here's a simple example. To get input and output, it's the first thing we do whenever we have a new system. I design a new piece of hardware. I design a new hardware software system. You work for a company that makes things. You just want to get the talk, right? You want to get some output. If it's a hardware device, a sensor, you want to get some bits coming out of it and see, is it alive? Is it talking? Is it working? So we do the same thing called hello world. So how do we get data in and out from a processor to a console or the device that we can figure out what's going on? We use something called syscall. Syscall is short for operating systems call. Syscall. So in this class, we concentrate on designing the control unit, designing the data path, designing some memory systems, I/O devices. This is operating systems class. We just use it as a service. So how do we use it? We load some registers with different service codes that tell the operating system what to do. For example, suppose I want to display an integer that's stored in the T0 register on the console. Well, I got choices. I can just display it in binary, or I can display it in decimal. Well, so what do I do? So I want to display it in decimal. I load a 1 into V0. Load immediate. So this constant 1 got moved. And then I have to say what register I want to print, because there's 32 choices. To print a particular value, this is a service code, is actually control information. What's contained in this register is the data to be printed. That's just their convention. That's how they defined it, the people that wrote the people that wrote the operating system, the computer scientists, okay? The programmers said that when you call the operating system with this, we call it pseudo instruction or assembler directive, it's actually not a machine instruction, it's a subroutine. We'll explain later. But syscall, when syscall is executed, it looks inside V0 to figure out what to do. And it looks inside whatever is specified here, for example, A0, to say what data to print. So this is control information. This is the data. We'll give you an example. So here's our first assembly language program. The simplest one I could think of is to decrement a value by 1 that the user enters on the screen. You're going to do this in lab. Next week, we're going to actually put this in Mars and get some output to the screen and start to work with these. You'll see here that what's highlighted are the actual functional machine instructions. The rest is just loading things and configuring for input and output. We have some comments. We like to comment each instruction because it can get complicated. And we're starting off easy, but later, how we encode data, what the registers mean. Is this saying the value for A or the value for B or the value for C or something intermediate? We like to keep track of these things. You hand off your code to the next guy and they know what you're doing. Yeah, good.
Is this called like jumping down into kernel mode?
Yes, it is.
Okay.
Exactly. So syscall is an operating system's call. Someone wrote some routines, and you may use the word kernel or user space for some subroutines to output data, either input or output subroutine. We also have some comments. We call this a header. In the header block, it's always good to say, what does this program do? What does it not do? Maybe you got busy, you were only able to take it so far, and then you get moved to another project because you got promoted, which is good, but then someone is mad at you because it doesn't work. So you just say whatever it does and what it doesn't do. We don't be afraid about that. We point it out there, and it saves us trouble later. So this is a positive example. We'll give you more positive examples when you design the project. We have a couple project submissions. It's done incrementally in the lab. I like to give you a positive example what a complete program would look like, to showing all these components. We give you a rubric that says, so many points for this, so many points for that, so everybody's clear. But this is a small example to get started. What does this program do? User enters an integer on the keyboard. The value is decremented, and the result is displayed on the console in decimal. So if we look at this, we have data segment, which is constants, and we have text segment, which is instructions. We know these are all stored as bits. Each one of these is stored as bits. These are character bits, right? ASCII code we'll have covered in another module. This instruction, pseudo instruction ASCII Z, means take the string, convert each character to an ASCII value, and 0 terminate it. If you take a class in C language, every string in C actually has a certain character at the end. What is that character? It's a backslash 0, which means end of string. So this is putting a backslash 0 at the end of this for us, and it's telling us it's the end of the string. That's what ASCII Z means. In this program, what does this do? It adds together, it's kind of interesting, 0, which is the value of 0, and the constant 1, and puts that into T0. This is another way of doing LI. Why? First I had to tell you add I is add immediate. It's the same as add, but one of the two operands is a constant. So why is this equivalent to, semantically equivalent to LI T0, comma 1?
0 plus 1.
Add 0 to anything, it's the self, right? So we add 0 to 1. That's 1. It stores 1 in here. No matter when I run this, 7 in the morning or 3 at night, or whatever time it is, it's going to have the same result of putting 1 into T0. It's another interesting thing. There's more than one, as we see again, more than one way to implement the same functionality with different machine instructions. So you're going to say, well, why didn't you just use LI? Well, you could. I'm just trying to show you this plurality of execution. What are we doing here? We're getting ready to output the prompt. What's the prompt? Please enter an integer. And then we call syscall, which is saying control code 4. And how we refer to these instructions is by their address. Their address is specified by the programmer using a label. A label has a suffix of a colon. So, for example, here's a label A and a label B. We saw some examples of labels already. Label can be a label for a string. In this case, label is a numeric value. How many words of numeric value? 10 or 20 is reserved. So what this is doing is zeroing out 10 words of memory. A word in MIPS is 32 bits, which means 4 bytes. So this is reserving 40 bytes of memory, which is 10 words. This is reserving 20 words of memory, which is 80 bytes. So we see other examples of a label. That's label A and label B. We saw an example of a label here. Labels that are for data items or in the data segment. So for example, prompt is a label. It's the address of the first character in the string. So the string is stored in memory, which we'll see very shortly. And when the string is stored in memory, each character is stored as a byte. We can actually see it. We'll look at that. So this is the address of the prompt string. This is the address of the answer string. And ASCII Z will have a 0 terminated, which is a Z ASCII values for each element of the string. So labels refer to an address. Labels can refer to address in the data segment, which is a variable or a constant, or it can refer to an instruction, which we'll see. We need to use that to branch, tell where we want to branch to. We'll come back to this. But for example, in my .text segment, which is instructions, what this is saying is that if these two registers' contents is not equal, branch to label. So label is an address that I want to branch to. I put a colon with some tag, and the assembler is going to make this mapping. So you're going to say, okay, I'm not sure what's going on here. Let me give you an example. Here's a program. And you can do this on the slides too from the PDF. It works just as well, maybe even better. Is I can select all this text.
Control A.
Yes, Control A sounds good if it'll let me do it. Okay, okay. And paste this into Mars. So this is what you're going to do in lab. If you had lab this morning, we got started on these. Since I'm covering some of these right now in lecture this week. So this is the assembler, Mars. I can make a new file and paste it in. So you can see that these are our opcodes, operands. This is immediate modes. This is a constant. These are comments. With the hash means comment. It color codes these so we can see what's going on. But you can see some of these may refer to labels. See? Load address, this is the address of prompt. Prompt is a string, will be loaded into A0. So what else is on the screen? That's the edit window, is the code that the assembly language programmer wrote. Here we see the register file. You can see the contents of these different registers. Mars will initialize most of them to 0. Some of them have special values, which we cover later. So as a courtesy, Mars will zero these out. In practice, you probably want to make them 0. We'll show you how to clear a register. But these are already zeroed out for us. So what happens if I save this? I get an option under the Run tab to assemble. Assembler did was to translate each one of these source instructions, which adds a line number, 25, 24, line number to each line of the assembly language program, to assemble these instructions. Sometimes there's a one-to-one mapping. So add immediate, map to add immediate. Sometimes these map to other basic instructions. So basic instructions are what we call intrinsic instruction. I wouldn't use the word basic, but that's what they did. But actually that means it's intrinsic, means it's implemented in hardware, inside MIPS processor. So that was our time versus space trade-off. In a real processor like MIPS, you have 100 or so instructions. We'll learn maybe 20 or 30. But you can see the instructions here is what the machine actually executes under BASIC, means there's hardware to execute each one of these. Sometimes, though, we specify things for the programmer's convenience, which are mapped to different hardware instructions. It could be more than one. So you may type one instruction here, which we actually call pseudo instruction. Pseudo instruction means it's not intrinsic in the hardware. So we actually have to have multiple steps. That's a time versus space trade-off. Yeah, we could add hardware for it, but maybe it's not worth it. We can just execute 2 instructions instead of 1. That's up to the designer. That's some trade-off. So this column is what the actual machine code statements that are going to be executed look like. And here, this code is a machine code written as a binary number. These are hexadecimal representations, but each one of these is 4 bits, right? So help me translate the first instructions machine code to binary. This is what's sought, right? Translate the instruction. We're going to do this in another module soon, but we get you started on it. And it's good for today to talk about store program concept and how instructions are stored as bits. Translate ADDI, add immediate, T0, $0, comma 1, to its corresponding bit pattern. So with Mars, it makes it easy for us to answer this question, because here's the instruction as assembly language instruction. It got translated to this. Well, T0 is 8. If you look in the table, T0 is, in fact, register number 8. Register 0, 1, 2, 3, 4, 5, 6, 7. 8 is T0. We said that register 0 is hard-coded to the constant 0. It's actually the only register that doesn't have flip-flops inside the register file. Why? Because it's always 0. As electrical engineers, if a value is 0, how do we express that as a voltage? 0 volts. So all the bits of register number 0 are grounded. They're just connected to ground. You don't need any flip-flops to store any bits because it's always 0, and that's how we make it 0. He says, is it that simple? Yeah, we just connect the wire to the ground plane, and then that's representing a value of 0. If we load a value from that register, it's just setting them all the voltage levels to 0, which means 0. Register 8 is T0, as we said, and we said that this column is representing the machine code. So what I need to do is translate this from a hex representation to binary. So let's look at some execution in this window, which you're going to do this in lab, and I get you started here in lecture, but your lab assistant will help you step through this in more detail. So this was the text segment. What about the data segment? What we're looking at here is actually data values stored in memory. So this is the processor's contents, and this is the data segment is looking inside the data stored in memory. It doesn't look like much here, but what we can do is click this box, and you can actually see the characters of the prompts, 4 letters at a time, stored backwards, which will explain why they're stored backwards later, okay? But these are the data from the prompts. So if we look at the program, we said, please enter, so we see ENT. We can actually see ENT, please, see please, PLEASE, space, enter. We'll explain how these are encoded. Each one of these is a byte. A byte is a character. But in MIPS, each one of these is a word, okay? How many bytes per word in MIPS? Is 4, because it's 32 bits per word. Word is 32 bits in MIPS, and each byte is always 8 bits, so we actually have 4 bytes here. This is something called little endian. There's little endian, big endian, we'll explain later, but there's a certain order in which the bytes are stored within the word. But this is showing some of the constants here. So what can you do with this assembler? So we assembled it. Then we can run the program. Run is go. We'll start the execution. So it's asking me to please enter an integer. And the point of this program was to do what? It was decrement, right? Decrement whatever I enter by 1. So I'm going to go to Mars. And put in the value 5. Okay. I press enter. Decremented value is 4. You're going to say, well, it happened too fast. I can't see what it's doing. That's the single step mode. You can go to step mode and look at this instruction by instruction, and you actually see these registers change. Some of these changed. If we look in the program, the final value was contained in A0 because that's the register that outputs it. If we look at the code, we'll step through, we'll show you a step. But look at the code. How do we print out a value? Well, we have to use a service code for print integer. Print integer service code is 1. That gets loaded into V0. You're going to say, well, how did I know that? You use a table. We don't ask you to memorize it. Use a table. Functions. So to print a string, I use function code 4, and I load into A0 the address of the string I want to print. That was, the answer is such and such, and I'll show you that. And then that's the first step. I print the header, which is text, and I print the value. The value is an integer. So I use print. I want to print in decimal. I can also print in binary. When I call syscall, I put a 1 into V0, and then whatever is in A0 is what gets printed. So we can see that happening in the code. And then we're going to step through the program and watch it occur. These are the steps that the hardware actually executes. So you can see the final result got moved to A0 because we want to print it. Then we set the code to 1, which is printing out the integer. We already printed out the answer prompt, which the answer, the decremented value is, got printed here with this syscall. So those 3 instructions work together to print the text. And then after we calculate the answer which is put into A0, because print integer looks in the A0 register, this statement, these 2 instructions will print the value, whatever it was, 4 in this case, which is the contents. We can look inside this register file. Is 4 is the answer we want to print. So you're going to say, okay, I see how to run some machine code here, but if I want to see each instruction execute, assemble it again. And then if I use step, we'll go 1 step at a time, which is 1 instruction at a time. So after the first instruction completed, and it's going to mark it green every time this updates. So this instruction just completed because yellow is going to execute next. So this is done. What did this instruction do? It took the constant 0, because this register 0 is hard-coded as 0, added the constant 1 to that, and then stored that into T0. So when this instruction gets done executing, I should be able to look inside T0, which is register number 8, and see the value. Sure enough, it's there. Suppose I want to see the state of the system before that occurred. You can actually go back step. So before this first instruction executed, register T0 was 0. After it executes, T0 goes to 1. This is another way to step. Then what? Load V0 with 4 because 4 prints a string. So before it executes, we see V0 has a value 0. After it executes, it's loaded with 4. So this is giving you a way to see the actual machine hardware instructions that are executed when we execute any assembly language program, and it's showing the changes to the register file. It turns out the register file is all we can update when a processor executes an instruction, unless we use load or store. Load or store send a value, brings the value in or sends it out to memory. We're going to cover that soon. So here's a way to take code and figure out what's happening. You could take any of the code, any of the examples, anytime you're not sure. You saw an example, but you weren't sure how it worked. That's normal. One way to help understand it is scrape the code from the slide, paste it into Mars, and try executing it and watch the state of the register file change as each instruction is executed. And you can also see the program counter increment. Okay? So when this program started running, see, each one of these binary patterns for each instruction stored in an address. Question, why does the address go up by 4 instead of by 1? This is just one instruction, so this is the first instruction, is at address 0, and the next instruction is at address 4, because 0, 1, 2, 3 is the address going up, because memory is byte addressable. How many bytes here?
4.
So program counter actually increments on a real machine by 4. Remember we did module 2, we incremented the program counter to go from one instruction to the next? Well, it was a hypothetical machine, it was just moving from one statement. It had a red arrow, right? A red arrow pointing to the next instruction to execute. So this is pointing to the first byte of the next instruction to execute. That's what we're seeing here in yellow. It's the next instruction. Look at the program counter, yeah, you can see it. What do you see? An address. See, this is displaying in decimal. I think I can change the representation of these. So this is the other thing to know too, is you can change your viewing, like we click this box for the ASCII. You can look at things in hex. Now we see address 8 written as 32 bits value, which is 8 hex digits right here. What's going to happen in the next instruction? Well, I'm going to go up to C. C in hex is what in decimal? Nope. 9 is 9 in decimal or hex. A is 10. B is 11. C is 12. Which is 4 more than 8. So let's go to the next instruction. And you can see now the program counter went to address C, which means the next instruction to execute is grabbing bits, grabbing these bits. Well, it's a coincidence. Okay, but in any case, that's 000C. You can see at any address is actually the bit sequence for syscall. So we'll do more examples of these, but this allows us to visualize the execution at the hardware level, and we're going to make these voltage levels in bits. So let's try a few more constructs so we can make a more interesting program. One of the constructs that makes computers powerful is the ability to make decisions based on the data. It turns out that no matter how complicated we make the code, there's only 2 instructions in MIPS, which can execute any program. Is this testing if 2 registers have an equal value or not? It's so simple actually, but since everything's coded as bits, we can check if the bits are equal. So the semantics of BEQ RS, RT, L1 is that if the contents of RS equal the contents of RT, then I'm going to branch, which means the program counter gets set to the address indicated by L1. L1's a label. It's a label in the text segment. It's telling us where to branch to. Branch means conditional. If there's a branch in the road, take it. All right, so, well, here's a branch in the road, and if this condition is true, I take the branch. If not, I'm going to go to the next instruction, which is the normal thing the processor does. It keeps incrementing the program counter by 4 in MIPS to go to the next instruction, next instruction, next instruction. We just saw it, right? We went from 0, 4, 8, C. It was the next instruction, next instruction. That's what's going to happen here unless these two register values are equal. Then we set the program counter to whatever address is specified with L1, which we're going to show you. Or here's another instruction that does a branch called branch not equal. If the contents are different, I go to L1. If the contents are the same, I go to the next instruction. I keep incrementing going down. Same when we write C code, right? If it's an if-then statement, if, then you do the then you go on to the next instruction right below it, right? Same thing we're going to do in assembly. We also have unconditional jump. Unconditional jump uses a J mnemonic. Mnemonic helps us remember what it is. See, branch equal. It's not really an acronym. It's branch and equal, branch not equal, which actually is an acronym in this case. And here's jump. So JL1 is unconditionally making the next program's statement that's executed, which we call instruction, to be at the address L1 rather than the next instruction in memory. So let's see some examples. Here's a C statement testing the equality of I and J. And if I equals J, then we set H to I plus J. Suppose I does not equal J, we do nothing. In this one statement, we go on to the next statement, which is down below it, right? In the C. So suppose it's given to you that the value of I resides in register S0, the value of J resides in register S1, and the value of H resides in register S3. You're going to say, well, how did it figure that out? The assembler keeps track of that for us. There's some rules, but for right now we're just going to accept it, and then we'll explain in more detail later. What's sought is the MIPS code that's isomorphic to the C statement. These are MIPS instructions. It turns out this one C statement needs at least 2 MIPS instructions.